Hello, I'm Abinel, and this is my video presentation for Physics 2212 Lab 3 Magnetic Field of Permanent Dipole Magnets. So first, we're going to introduce this lab. The objective is to find, measure, and explain how magnetic fields are created by a bar magnet and understand the distances reached by those fields. There are four main fundamental principles that will be used here. The first is the Biot-Savart law, which can be seen right here in this equation, which is going to be used to find the magnetic field in either a wire or you can use to derive the equation for a dipole. We also have the idea of superposition, which is pictured in this visual right here. The main idea of this is where you have three separate objects, in this case it's magnetic fields, and to find the sum of the holes from the parts, which is, say this is field 1, this is field 2, and field 3, you add them all together to get a final superposed answer. So in this case, we're going to be superpositioning the magnetic field of Earth and that of the bar magnet to get a net magnetic field experience at a point. We next have the magnetic field of a dipole, both on and off axis, which is important, as we'll see later, for our linear regression graph to solve for the distance coefficient of our magnetic fields, as well as the perpendicular, which will be used to solve for the field at various different points. And finally, we have the magnetic field relation from distance to observation point, which is seen right here, where the magnitude of the bar is equal to kr times any arbitrary constant n, which should be negative, as when the bar is moved away from an observation point, the field should get weaker at that point, as it is over r cubed. So the greater the distance, the weaker the field. Now here we observe the behavior of bar magnet versus traditional dipole's electric field. Think of the north as the positive, south as negative, and the field just goes like this in a circle, as like, because it's treated as a dipole essentially. So it's the same right here. You can see it follows the exact same pattern. So if you get confused, think about the direction of a field for a bar magnet or dipole, just think of it as an electric field dipole. And the field lines, while it's not the same in theory, it's the same conceptual lines, which kind of is a way it helps me think of it. Here's a preview of my results. Our n is equal to the slope of our linearized graph, which is ln of our magnetic field versus ln of the distance. And in this case, it came out to be negative 2.823. And our mu mag constant is 3.86. So initial observations made for this lab are when the magnetometer is far away from the magnet and measures a near zero magnetic field in the x direction. This is true, as it should be very far away, meaning there should be little to no influence by the field. As it moves close to the magnet, the measured x component should decrease. This is false, as r decreases since in the denominator, then the magnetic field will increase as r gets smaller. The position of the magnet does have an effect on the measured x component of the magnetic field as it changes the r value. As the magnetometer moves close to the magnet, the measured x component of the magnetic field will increase, as it's the opposite of part 2 of this. Attached right here is our data for our x-axis magnetic field used for linear regression. Feel free to pause here and read through it. Basically, all we did was take the magnetometer of our phone at different distances away from the observation point, our 20, 70, 120, 70, 220, and record those fields, and then take the ln of both our radius and of our field and just graph that. And right here is the data for our off-axis magnetic field used for Glowscript code modeling. Feel free to pause any time and read through this. Here's the graph of ln of bx versus ln of r for our linear regression. You can see right here the slope is negative 2.823, which is our n value. Yeah, that's about it for that. And right here is my Glowscript code, which I'll walk you through real quick. So this first section right here is just used to model the magnet. Let's make a little gray cylinder for that. Next, we need the magnitude of our magnetic moment, which is we calculated earlier in the lab. Right here, this equation creates a function for our magnetic field, so we can visualize it. This right here is just scaling, so we can actually see the arrows properly. And then lines 54 through 60 create our observation locations based on what we have recorded in class. Next, we create our arrows towards our magnetic field on axis and perpendicular to the axis, which is just standard arrow equations. You can edit the color of the axis for each one to differentiate them. Then we have to visualize our magnetic field 45 degrees off axis, which we take our d-perp from our experiment, which came out to be 0.18, and we plug that into the following equation, which will draw an arrow to represent the magnetic field 45 degrees from the axis. This is the result, with the orange being the direction of the magnetic field parallel, the blue being the magnitude and direction of the magnetic field part of the perpendicular, and the purple arrow right here representing the error of 45 degrees off. And feel free to pause and read here. You can see our D value calculated, and all the B values match up with the tables previously shown. They're very close. Now we have our what-if questions. Say we had not oriented the experiment to compensate for magnetic north, and instead just lay out the mirror stick at some intermediate angle with respect to Earth's magnetic field. How would the results have changed? Each result would shift by the exact same amount as the angle formed with respect to Earth's magnetic field would equally impact some small factor, and when we compare our experimental results to our theoretical, they will be more different than they currently are. Secondly, if we run this experiment again and stick two identical magnets together end to end, how would our measurements results differ? Our magnetic field, the answer is our magnetic field would have the same direction at all points, but be stronger as the superposition of the two magnetic fields will combine to make one larger field, which is the same direction but stronger at each point. Thank you all so much for watching my lab, and have a great fall break.